Hello, everybody. Welcome to C++ Russia Online. Thank you very much for attending. I'm sorry I can't be there in person. As you can see, this is a talk about a performance analysis of a simple trading system. It is a very, very simple system. Let me give you a bit of background in case you're unfamiliar with the world of finance in London. This is a very specific talk about this area. So therefore, there'll be many things that do not affect people in the general world, but there will be many things that do affect some people. So one must be careful with what one takes away from this because it is quite specific. But I think there is some interesting background and interesting issues. Now, background. In the area I work in high frequency trading and low latency trading. There are many issues surrounding this, and I'm going to look at some optimization case studies. So I'm going to look at some particular examples, the impact of the compiler, the operating system, and the hardware. So for example, in compilers, we've got performance quirks in various compiler versions. Then we're going to look at static branch prediction, its use and abuse. Many people are very worried in the HFT world about static branch prediction. Switch statements, can they be optimized? And then what I'm going to look at is C++. We can use template metaprogramming. Let's go mad and see just how extreme an optimization we can try and implement, and let's see if that has any impact. Then what we'll do is put it all together into this very simple trading system. It's called a fix to MIT bit translator. Fix is a messaging protocol used in the financial community. It's very old. It's ASCII based, name value pairs. It's not very good. The MIT bit is a binary message format for the Borsa Italia exchange in Italy. There's going to be a lot of graphs and a lot of fun numbers and figures. So we'll take a break. A few issues from Clang, because everyone thinks Clang is wonderful. Well, maybe. And then what we'll do is we're going to have a look, because what we've been doing is looking at the software. But what about the operating system? What about the hardware? What about the impacts of the operating system? And we'll look at the results of this piece of software, the fix to MIT bit translator, and see how that was impacted. And then we'll try and come to some kind of conclusion. So, HFT trading. There are many opinions, but this is mine, having worked in the field for a little time, since about, I've been working in the city since 2004, and I've worked in HFT trading since maybe, crikey, 2000, crikey, high-speed trading, 2012, earlier. So what we want to do is, if we place a trade, can I beat you to the market? Because the point is what I'm doing is I'm trying to discover a price that's advantageous. Everyone wants the advantageous price. So if we've got an algorithm that computes these prices, this is great. That's very clever. But what we can then do is speed it up to get it to the market faster and make a bit more money. So it's not rocket science. It's not safety critical. It's not airplanes or rockets or reactors. Nobody's going to die over this. They might lose their pensions, but they're not going to die. To be truly fast is to do nothing. One is trying to persuade one's boss that we don't want to do this because it will slow things down. It's always a pushback. There's always a tension. Moreover, it's not that tricky. It is just message passing. I'm copying bytes from an input socket to an output socket with some transformation, because I'm going from fix to MIT, these two message protocols, but also I might be doing risk checks and so forth. We want low-level control because we want to go as fast as possible. You guys are very clever. You'll be shaving off a clock cycle here or there. I need to shave off the clock cycles. So we want to go as low level as possible. Hardware and software will interact intimately, because the way I place my instructions in the instruction queue affects the way the pipelines can stall or not, the registers can load, etc. So we want to attune our assembly directly from C++. We want to write our C++ in a way that the assembly is optimal. Why do we not want to dip into assembly? Because it's hard. Of course, the hardware, if we're talking assembly, we need to consider the hardware. Multiple processors. We may have multiple processors on our motherboard. So we have processor 0 assigned to the operating system. Processor 1 is assigned to our trading functionality. We want multiple buses, so we want a memory bus per processor so we don't end up having contention accessing the memory. We may want to dedicate cores to tasks. Then there's the network infrastructure. There may also be bugs. We've all heard, of course, of operating system bugs. They're not all equal. Tool sets as well. Remember, it's all well and good for me to develop code that runs fast, but if it takes me 6 months to do it, I've lost that market opportunity. So I want to be able to develop the code quickly, and therefore I need a good toolset support as well. Configuration of the operating systems and hardware, C groups, ISOL CPU, performance tuning. This is all complexities and sophistications. We will discover that not all compilers or even versions were created equal. Which is faster? As in, when I say faster, which compiler is faster to compile the code, and of that code generated, which is the faster code that runs? I'm going to mainly focus on G++ and a little bit of Clang, mainly some maybe it's a little bit of ICC, Intel's compiler, and I'm mainly going to focus on C++ 17. This is a typical chip that we might use. It's an AMD Bulldozer, circa 2013. It's quite old. Why? Because banks tend to have a lot of hardware they've spent a lot of money on, and they don't tend to upgrade it instantly. Hedge funds will use faster computers. This, of course, is old even for banks, but never mind, it's instructive because we've got lots of detail. What am I interested in? We can see the L1 instruction cache, top left. 64K in size. If we look down at the bottom, yes, we can see our little data caches in the integer cluster 1, integer cluster 2 to the left and right in the little corners. It's only 16K. It's much smaller, our data cache. Our data cache is a vital commodity. Moreover, to get at that data in the data cache, we're all the way down the pipeline. Whereas if the data could be put in the instruction cache, then we're right at the top of the pipeline, right with instruction fetch. So things can work. You can see I'm being very, very trivial and waving my hands here, but things can work in a simpatico manner. Also, as I mentioned, bugs. We had Meltdown and Spectre appear a couple of years ago, and this has consistently impacted processor performance. How might this impact our trading system? So I had a look at that. Billions of devices are affected, as we're well aware, and as we have seen with lots of patches, kernel patches, we've seen performance issues, etc. Now, okay, this is a C++ conference, so I'm going to talk about C++, and we're going to want to optimize it. Remember, I'm going to ignore AMDAL here, 9010 law. I'm going to say, you know what, I've done all my profiling, I've run valgrind, I've decided I'm going to optimize the software because I can't touch the hardware, that's infrastructure, I can't touch the operating system because that's IT support, and therefore the only thing I have available to me is tuning my software. As we know, it's non-trivial. We've got, and we're going to see performance quirks in compilers, etc. I've gone through this. So let's skip on. Let's get into it. Performance quirks in compiler versions. They normally improve with versions, don't they? This is normally what we might perceive. Here's some example code. Why am I interested in this? What's going on with the source string? Static const char. Right, this is static, so it's internal linkage. Const char, this is very old school code. So what should happen in this is what I would like to see, is I would like to see that dest has the string 0, 1, 2, 3, 4, etc. in it. At compile, after compile time, at link time, that's what should appear. Why? There's no runtime. Yeah, memcopy is occurring at runtime, but this is all static. There's no variation. So let's look and see what the compilers do with O3. GCC, very old version, 4.47. If we look at this, this is quite interesting. We can see the two move abseeks. They're next to each other. Now, we know this is usually a bad idea. Why? Because if we reflect back on the bulldozer diagram, we may end up with a hardware hazard where we've only got one unit that can handle move abseek. So we may end up with a stall. We'd probably want to use that move L between the two move seeks. But what's really interesting is notice the strings there. Yeah, that 39784 blah, blah, blah. That's all in the instruction cache. 0 clock cycles to access it. The only clock cycles taken here are to do the output to dest. This is half good. I'm not so unhappy. But 473, look at this. Now, the source string is on the stack. So it's had to go into the data cache. Remember, that's all the way at the bottom of the pipeline. Therefore, we have to wait for it to load. It's expensive. Typically, access to a register is 0 clock cycles, 1 clock cycle at most. Access to the L1 cache can be up to 10 clock cycles. Yes, that's frightening. So we've had a serious performance loss here in a newer compiler. Okay, what about other compilers? We can see in 481 it's recovered, and we see some stability. But then in the 7 series compiler, right, remember I did an march. So now what we can do in the 7 series compiler, we've got vex instructions. So we can see vex instructions are used. We can see the move has been moved between the vex instructions for better scheduling. But the problem is vex instructions don't have immediate operands, whereas the move seeks do. So the change to using vex instructions has cost me. Why? Because I now have to put things into the stack again, into the data cache. So you win some, you lose some. I've got pressure on the data cache. I've got using vex instructions. So I'm using the pipeline nicely. What's the result? It's complicated. Again, GCC 8.1 uses slightly different instruction encodings. Move DAX 64, you see. So this is again very interesting. So the big problem is as well, is we can see with GCC with all these versions, it's very unstable output. It's highly dependent on the version, the output. Therefore, the performance could be very dependent on the version. This is almost like Alice going down the rabbit hole, and we wandered down this rabbit hole and looking at compiler versions, and suddenly we've got this simple test, memcopy. Look at it. It's mad, isn't it? Okay, what does ICC do? Well, we can see ICC, it's reasonably stable. We've got 2 different sorts of outputs, but the problem is ICC still uses the stack. Why? Because it's using vex instructions, no immediates. Clang, very stable output. Look at it, it's exactly the same output, 3, 5 to 10. The 2 move apps are right next to each other, which is very poor scheduling. The move L could be moved between them. That's not being done. Again, we're forced to use the stack because of the use of instructions, but at least it's a stable output. How does it impact reality? Can we actually measure a performance difference with this code? Okay, we've got a complicated graph here. Notice the Y scale is a log scale. Also notice some of these are running infeasibly fast, 10 to the 14. Right, this is operations per second, 10 to the 14. My chip is a 2.6 gigahertz chip. What this means is that the benchmark was optimized out. The compiler managed to optimize out the benchmark. And this is perfect as far as I'm concerned, because everything happened at compile time. This is what I want. So I want to see those spikes because it's telling me the compiler could optimize out my code. What I did is I wrote my own implementation of a small string optimized string. And what we can see here is the different test types on the x-axis. So on the x-axis, we just construct and destroy this small string. And we can see the vast majority of compilers can optimize this out at various versions. This is great. But Clang 6 can't. You see? Clang 9 fails again. Most interesting how some of these newer compilers can fail to do this, and yet they can also optimize it back in. Again, we can see as well that the small string equals, we can see much variation. Small string replace, most compilers can't optimize this at all. Only 1 or 2 compilers can actually optimize out the small string replace. So this means that we need, if this is critical to us using strings, our choice of compiler is very, very important depending upon what operation we're using, because sometimes our code might compile to nothing. And this is wonderful. We've done something, we've met business need, but we could compile it away at compile time. Why? Because it turned out that need, that flexibility was not required. Okay. What about static branch prediction? Most important, why am I interested in static branch prediction? The reason why is when a trade is placed, in the morning, usually with an algorithm, and this is a new order. Then what happens is during the day, the behavior is this order is modified. So we get a modify, 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 a whole chain of modifies. And then once in a blue moon, we'll get an execution coming back. And that execution is the money. So in other words, our code by branch prediction has been conditioned to run optimally on the processor for the modifies. Whereas I don't care about the modifies in performance. What I care about is getting that execution back to the client as soon as possible, because that's where they make their money. And they need to know this as fast as possible. So what I want to do is abuse my static branch prediction to change it so that the most important path to me is in the fall through. So, okay, let's look at some history. There is a rule called the BTFNT rule. Backward taken, forward not taken. This comes from computer architecture back in the 50s. And the idea is it's backwards taken. When I generate code, there's desugaring that goes on. And what happens is loops always have a backwards jump. They're always transformed to a jump backwards. Whereas forward not taken is if then else, that's a forward jump. Intel added some operand prefixes, and what happened is these would tell the processor which is the likely branch. So if I had a forward jump, would it be the else or the then? With a backward taken, would it be a fall through or would it be a backward jump? But they're now ignored by the Intel architecture. Superscalar architectures suffer very badly from misprediction. And it's called the pipeline rollback. It can cost 20 to 30 clock cycles. It's very, very expensive. So we really, really want to tune this. We could use built-in expect. They were introduced to omit those prefixes, but now they just guide the compiler. The fall-through should be, in our little if, should be bar 1, not bar 2. This is computer science law from academia and hardware. So here's our test example. Again, I keep these very simple. I use Godbolt a lot to look at the assembly. Thank you, Matt. And I like to keep them simple. Why? It makes it very clear when you do changes. So here we can see GCC. This is very, very interesting. If we look at the 482 to 5 on the left at 01, we can see JEL2, this is a forward jump. So this means the compiler is going to fall through to the bar 1. The superscalar architecture will fall through to bar 1 before that test B is completed. Forgive me. Now, if we look at 6.1 to 9.3, JNE called bar 2 at 01. Hang on, this is swapped round. Our static prediction is swapped to the incorrect one. Now, if we look at more versions of GCC, right, we can see at higher optimization levels, it's flipped round. Remember, we had it 01 for 4.8, it was L1 first. It was bar 1 first. Now it's bar 2. So in other words, with the same compiler, if I change my optimization level, my fall throughs change, my performance profile changes, my branch mispredictions register counts change, and so forth. This is a serious problem. If we look at GCC 8.1 to 10, oh my, it's changed. It's down to the correct way. Back to the original, as it should be. Bar 1 is the fall through. I actually had a bug report open on this for many years saying, what's going on? Why is it flipping at the change of optimization level? It turned out that there was a -1 involved. The percentage probability of the bar 1 being emitted before bar 2 was 40%. And what happened is when you changed optimization level to 02 and 03, it was 1 minus 40%, 60%, so that meant it flipped it round. Curiously, the fix was done, but nobody notified the bug reporter, or the bug report wasn't closed. I came along later and closed it because it seems to work now. Now GCC finally works properly. That's frightening, isn't it? Many, many people have learnt the wrong rule because of GCC. Okay, what about Clang and ICC? Do they get it wrong? Well, ICC, look, we can see all versions 13 to 19. It's exactly the same code, identical code, bar one first. Clang, versions 3 to 10, likewise, consistent. GCC, if I use GCC and I optimize for GCC various versions, I might end up flipping the static fall through to get it the best performance. But then if I change to use Clang, I now need to re-optimize my code. Okay, I'm going to use built-in expect with GCC at the moment, and I'm going to see, does it make a performance difference? Again, I've got my small string optimized string. The reason why I'm talking about strings so much is because recall fix protocol, it's an ASCII format. So I'm doing lots of, I'll be copying small sections out of it. I'll be converting doubles in there to a string of double to a double value. I'll be converting an integer, 1, 2, 3, 4, 5 string into an int and back. I'll have to be creating strings and copying strings into there for, say, the ISIN code, which is a string. I'll have to copy that in. So it's very important to me, these small string optimized strings, because there's lots of small strings in fix. So this is why I'm very interested in this performance benchmark. And we can see that, yes, indeed, built-in expect has a material impact. Not the way we'd expect, though. Look, if we look at the graph on the left, small string constructor destructor, we see a performance loss. Again, if we look at the assignment, small string assignment, within these error bars, I would say there's no statistical difference in performance. Again, if we look at newer versions, 5.3, we can see the performance has changed. 5.3, there's no impact on using built-in expect. And oh, by the way, at 5.3, I tried changing the ABI as well to ABI 11 from, remember, this is an older compiler, from the ABI 09 to the ABI 11 to see if there was any impact in changing the ABI. No, there wasn't. Which it shouldn't be, because I'm not using the small string from C++. I'm not using standard string. Now, what's interesting is that performance loss in the constructor-destructor, the only change I made in my code was in the destructor. There's an if statement that says if the size of the string is less than the small string, is greater than the small string size, we're on the heap and we need to delete off the heap. Clearly that's an unlikely, so I should have a built-in expect. This is unlikely. Why? We're a small string optimized string. We're going to be used for small strings. So clearly I want that to be ignored. I want that to be jumped over and ignored. When I added it, it slowed down the code. Madness. I had an obvious optimization which must speed up the code. It actually slowed it down. Okay, what about different versions of GCC? If we look here, GCC 6.3 on the graph on the left, we can see, hang on, it was optimized out anyway. So those big numbers there, we see at small string assignment, that's optimized out, we can ignore it. We can also ignore the other one, small string constructor and destructor. It turns out that the newer version of GCC can optimize out my test cases. This is great, I love this. Right, let's expand it, and what's happening with the 3 results on the right-hand side. So I put them on a log scale, and we can now see small string replace on the graph on the right-hand side. We can see there's a performance difference now between using built-in expect and not. And yet again, using built-in expect reduced, in an obvious way, reduced the performance. So what we've got to conclude here is that the use of built-in expect has some very odd feature in the code. I apologize, I didn't have an opportunity to look at in detail at the assembly. Well, we've seen some of the assembly for this, but I didn't have enough time to look at all the assembly for this, because I do this in my own time and it takes a lot of time. Okay, what about, we can see, added to the structure, we've got no statistical effects previously, but now we're going to look at GCC 7. What's happening here? Again, we can see basically everything's optimized out on the graph on the left, these big numbers. So these 3 smaller numbers, what's happening here? Let's have a look at the graph on the right with the log scale. We can see here, GCC 7 series, we've got 7.1 and 7.3. And what we can see here is that GCC 7.1, with no built-in expect, was faster than GCC 7.3. with or without built-in expect. And when I added built-in expect to 7.1, it slowed it down to that same performance. Curious. Newer versions of GCC, likewise, we can see here more benchmarks are being able to be optimized out, which is nice. We see an improvement in the compiler, const extra is being used. This is what we would expect. So, okay, let's look at the figures on the right with the log scale. And again, we can see that certain uses of built-in expect confound the compiler to the extent that it can no longer const extra optimize it out. So in other words, the use of likely or unlikely could be a major performance loss in your code. Okay, what about newer versions? We'll carry on. Newer versions of GCC. Oh, good. Look, at the right-hand side, look, this is all basically being optimized out. On the left-hand side, we can see that. On the right-hand side, now we can see that the use of built-in expect basically has no performance impact at all. The compiler can optimize it out, come what may. Good, it's fixed that bug in GCC 8. Yeah, fix that bug in GCC 8 where it couldn't optimize it. Or is it a bug? No, it's not necessarily a bug. It's a feature, isn't it? They managed to make it optimize it. Again, GCC 10, we just basically see more consistent results based on the 9. Now, if we look at Clang, notice Clang 5 to 9. I put all the numbers on the same graph. Why? Look at it, optimized out on the left, those high numbers. If we look at the line at the bottom, we've got the log scale on the right, and we can see very, very consistent, basically built-in expect had absolutely no performance impact. So in other words, the use of likely and unlikely in your code, depending on the compiler, is likely to have either reduce the performance or have no performance impact. Who would have thought that? Of course, it depends on your benchmark, so measure with care. Okay, we've gone through if statements. A switch is basically a glorified computed go-to, isn't it? It's an if statement with a computed target. So, we've all heard the mythical preferred case label, haven't we? Is it the first label? Is it the default? Are they somehow magically the statically predicted fall-throughs? This is not correct. GCC users and ICC, well, in fact, Clang, GC, and ICC use a roughly similar algorithms. I looked at the GCC one. It's a very interesting, what's called decision tree algorithm, but basically it clusters them numerically, the case labels, and then it uses a binary search to find the correct cluster. And then what it does is it does a linear search through that clique of case labels to find the correct one. So basically, a switch statement is not an order n expression in terms of branches, it's a log n in terms of branches, which is cunning, a nice saving. There's no static prediction. Here's my simple example. Again, note contiguous labels cause a jump table to be created. This is what one would hope. This is good. These numbers were chosen by me, a human, so they're not random. They're human random. Let's look at the effect of built-in expect. From our previous analysis, in terms of the fall-throughs from the O1 and O2 on GCC, well, I would imagine there's no effect. And in fact, that's true. Up to GCC 8.3, there is no effect using built-in expect on the switch expression on which case label is chosen. But newer versions of GCC are impacted by built-in expect. So a likely and unlikely does have an impact in later versions of GCC on both the static fall-through in the branch and on switch statements. Clang, all versions, were affected by built-in expect. So this is interesting. Again, GCC is showing this erraticness in its performance behavior. Clang, a much more consistent code generation. Of course, the obvious hack for this switch label is to hoist the preferred statement the preferred case label, out of the switch statement, have an if statement, and then what you do is use the if statement, and then in the else you've got your switch. But the problem is, of course, is static branch prediction. GCC, I'm looking at you. Finally, it's got it right. Okay, these are very simple examples. We're halfway through the talk. It's very good. These are very simple examples. Let's look at a more complex example. What I decided, you saw the mem copy, and you heard me talk about fixed messages copying things. So I got very, very, very paranoid about the performance of mem copy. I mean, I wanted to show you, this is my own code at home, so I can write code that is as complex as I like to save one clock cycle. I do not recommend this for production use. Notice I have cut out about 1,500 lines of template metaprogramming to compress it into this one slide. You can see it all. There's a link at the end to my library where you can see the details of this. But basically what you can see is I've got this aligned unroller at the top. The idea is you can see source size, destination size, units. So you can see that somehow what I'm doing is I'm taking a stride and I'm doing a copy in take a stride, do a copy, and so on. Then we can see below in the middle of the slide, mem copy opt. And we can see char, source size, char, des size. Now, these are statically compiled const extra, so this is all good stuff. You know, these are not even, source size and des size are in the lexer, they're not even in the instruction cache yet. And we can see here, I've got this unrolled 256 opt result, and we can see I pass in the copy. So you can see there we are, I'm copying. Bit of funny, using lambdas to generate assembly. You can see underscore M256 there. So yes, you can imagine behind the scenes, I'm using intrinsics to access AVX, SSE, SSE2, etc. instructions. Okay, does it have any impact? Let's look at the generated code. Now, GCC 4.9, recall GCC 4.7 put it in the immediates, the string, which is really good. But we're using move ups here, because remember I'm using AVX instructions, so I have to use the stack. And we can see here I've got my two move ups. I've got a move Q, a move L. So you can see I've got a long move, another long move, a shorter move, a shorter move, a short move. So you can see that I've split up the string and I'm basically chunking it up into sets of moves. The code generation is not ideal. The two move ups are adjacent to each other. Whereas if we look at 5.1 and 6.4, the two move ups have been separated by a move abseek, and that can take an immediate, and the compiler's taken advantage of this. This is nice. So what's happening is I'm accessing the data cache with the first move ups. The move abseek is running with an immediate, covering up that stall. Then what happens is that move ups can start executing, and then the move abseek finishes, the next move up can start, whilst the previous move ups is still executing, assuming we've got no pipeline hazards for move ups units. And then we can go on to the move Q, move L on other instruction units. So it's nicely scheduled. We look at GCC 7.1, and again, it's also nicely scheduled. But where is it? Where did it? No, it's the same code. Great. Why have I got that there? Okay, sorry, erratum on the slide. I shall fix that. Thank you. What about Clang? Highly stable output. There's a move apps and a move ups next to each other, which I'm suspicious about. I suspect that they probably use similar execution units, but we can see that with judicious use of micro-optimization, we can force the compiler to generate exactly the instructions we want. Because trust me, I've got intrinsics in the specialized template specializations, so that's where I'm generating the assembly. And what I'm doing is I'm hoping that the compiler, the generated assembly can, in the later sections of the optimizer, be shuffled around to be rescheduled. But the problem is sometimes superscalar compilers, they generate the code such that it is inaccessible to the compiler to optimize at that stage. And this is what we're seeing. Essentially, our superscalar approach, our approach at generating assembly has confounded the instruction scheduler in the compiler. Okay, what about ICC? It's a cleverer compiler. Can it do better? And we can see, yes, it can. Look at ICC 13 versus 16. Look, you see the move ups are being separated by move Qs and move Ls. So now we don't see any performance loss there. And again, later versions of ICC likewise separate the move ups and move Ls, move Qs and move Ls. And indeed, the later versions schedule even better because the move ups is started first. So the slowest instruction is started first. GCC 17 just went mad for some. ICC 17 just went mad and generated loads of useless assembly that was effectively equivalent to this, but was disgracefully suboptimal. I don't understand why. Okay, does it have an impact? Apologies for crushing these graphs onto the slides, but I think the point is the shape of the graph. Based on what we've seen before, we can see GCC 6 and 7. Yeah, watch out, there are changes of scale and log scales on the right. Apologies for that. What we can see is that with standard memcopy versus move memcopy opt, the compiler, earlier versions of GCC, GC7, they could optimize out with standard memcopy, but they couldn't optimize out with my optimized memcopy. It's probably because the standard memcopy boiled down to an intrinsic in the compiler, which the compiler knew about. Okay, GCC newer versions, right? What happens if we can see here the memcopy opt and the standard memcopy, the performance is now roughly the same. If we look again on the right-hand side here, we've got, again, likewise, performance is effectively identical. So what's happened is our optimization has either confused the constexpra generator in the compiler, or it runs just as fast. So what this is telling us is sometimes micro-optimizations may look really good, but because they are not alone, they're in a much bigger code base, they may have an unexpected impact or not as much as we'd hope. So it is always, the point is, remember I said at the beginning, I'm going to ignore Amdahl's law. Premature optimization is the root of all evil. This is where we found it. I've got complicated code to do standard memcopy for the same performance or less. Okay, what about GCC 9? Well, GCC 9, again, no performance impact, consistent at least. What about GCC 10? Just like GCC 9, no performance impact, consistent. If we look at Clang, remember Clang used to be very consistent in its performance, but here we can see, look at on the left, the log scale here. Look how my memcopy opt likewise could not be optimized out as it could be. Remember the other versions of GCC, sometimes the memcopy opt couldn't be constexpra optimized out. And yet look here at the figures, we can see at bottom right, on the leftmost graph, we can see my memcopy opt has got a statistically significant, and remember that's a log scale, that's a big difference in performance. It's beaten by a significant margin standard memcopy. This is why I did it, because I knew that that particular case of string replace was vital to me. The rest I didn't mind about. Again, if we look to the right and we come to Clang 7, here, memcopy opt outperforms my standard mem copy. But if we look at later versions of Clang, we don't see this case. It becomes, you get less. But the problem is again, look, if we look, there are statistically significant results here. And if we look at the right-hand graph for Clang 10 here, then what we can see is, look, there's a major performance difference in constructor-destructor with mem copy opt. So the problem now is GCC looked consistent, there was no impact, or it made it a little worse. Whereas Clang is very variable. Maybe more consistent than GC is arguable. Now, I happen to know that my 4180s that I used for this benchmarking, they have remember, it's AMD Bulldozer 2013. They've got a very rubbish vector unit that's very slow. More modern hardware has a much faster vector unit. Those AVX instructions run much faster. So hardware may have an impact. We shall see. Okay, let's try and roll this together and take an overview. What we have here is we have, on the Y scale, we have operations per second. Higher is better. And remember that my processor is a 10 to the 9 gigahertz processor. So if we look at things above 10 to the 8 on the Y scale, we know that's optimized out. So that's wonderful. We want that. It's really good. Below 10 to the 10, this is actually executing. So this is bad. It's got to be as fast as possible. We can see that there's considerable variation in compiler versions. These are compiler versions on the Y scale, on the X scale. Newer on the right, Clang is completely at the right, GCC is to the left. And we can, that big dip towards the right is the separation, because that's Clang 3. And we can see that in general, compilers seem to have got faster. But there's a lot of little quirks. There's a lot of devil in the detail. Look at that dip towards the left, GCC 6.3, that yellow line dips down. Again, GCC 6.3, right? What I tried having symbols and no symbols in GCC 6.3. Was this a performance impact? No, it had no impact at all. In fact, one might argue, if we look at the two figures of GCC 6.3 next to each other, that the move to ABI 11 improved the performance. We might argue, if we look at GC 485 on the left, that adding symbols statistically improved the performance. Weird. Shouldn't have any impact. Now, again, if we look to the right, we can see code is becoming more const-expra, so it's being optimized out. This is very good. We can see the small string here. This is my small string, and I've compared to standard string. The green crosses a standard string. That's almost hidden. It's very low. The performance is appalling. We can look at Visa string, GXX Visa string, small string. This is, okay, right. Let's go back. Standard string, that's the reason why we've got the ABI 11, because to the left of the ABI 11 is ABI 9, the old ABI, non-small string optimized string. So standard string is super slow. To the right of ABI 11, it's all small string optimized string for standard string. So this should be faster. We've got GXX Visa string, which is it's a custom implementation of a small string in GCC that you can make use of, and it's small string optimized. And you can see its performance is very, very, very good. That blue graph, lots of it, I mean, it's only beaten by mine. That blue graph, lots of it, it's got very high performance. Now, I looked at small string sizes and then big string sizes. And if we then look at big string sizes, we can see again, performance is reduced a lot, but that yellow line we see dipping down, that's standard string. Even when it's got ABI 11, performance is not great. So we can see that clearly optimizations, remember before, all those optimizations I suggested for the small string, the mem copy, the switch statement, the branching, and so forth. When we roll them together and select judiciously, this does not have the branch prediction. The built-in expect in the destructor. But it does have the optimized mem copy, it does have the switch statement, and so forth. Oh, and by the way, all the other branches have been tuned with static fall-throughs. No likely or unlikely, just the code or in position. So we can see when we roll together all these optimizations, it actually makes a serious difference. We can see that for small strings, my code is amazing, blazingly fast. Many times it can be optimized out. It's great. And it's only beaten by visa string, GXX visa string, in certain circumstances. So this is very, very interesting. Again, compiler versions, we look, Clang has an equivalent speed to GCC in the generated code. This is also good. Now, these are slightly different test cases. The previous one, this was just for constructor-destructor performance. This graph, we've added assignment. So now, what's the performance? And we can see, look. The visa string performance has dropped considerably. The small string optimized string I created happens to maintain its performance. But we can see Clang here has moments of insight. Clang 7 could optimize out a GXX visa string. And also notice the performance here of standard string with newer ABIs. Some of those can even be optimized out. So it looks like actually with more sophisticated tests, is there such a difference between the performance for this code? Right, let's push on a bit. We can see more complex, because now we've got replace rather than just assignment, more complex code, less can be optimized out. We see fewer performance advantages, but there are statistically significant advantages. Using an optimized string like visa string, like small string, like my small string is much better performance than standard string. You see that green line hovering below, together with the yellow line, which is my big string of performance. Visa string really outperforms my code with big strings. So choose with care. Okay, this is this fixed emit EIT translator. So what happens? Oh, sorry. It converts these fixed messages which are ASCII formats, to these binary messages, and sends them to an exchange simulator. The exchange simulator sends back a message, a order acknowledged message, which is translated back to a fixed message and then goes back to the client. I used Boostazio. Many other optimizations were also used, and SSE and higher instructions. I did not use Solarflare or open-on-load drivers. They would have reduced context switches and would have improved performance. I mentioned this. The message is translated and sent to the simulator, responds with a fill, translates it back. Computer was both quiet and busy, with and without NUMA control. I use Gentoo Linux, a highly optimized kernel. Again, there's my AMD 418s. Oh, sorry about that. Right. First things first, Boostazio. What is the performance of Boostazio? And I wrote a very thin glibc wrapper to the POSIX sockets API that emulated it, the API for Boostazio. Notice first, the histograms largely overlap, so there's no major obvious performance difference. If we look at the standard deviations, they're both 5. If we look at the means, 23 and 22, they're both equivalent. Remember that these means and standard deviations are calculated for a normal distribution. This is clearly not a normal distribution, so those numbers should be taken with a pinch of salt. They're useful for comparative purposes, but really the histogram is important. Now, I remain to be convinced that there is a statistical difference between my optimized glibc super thin wrapper and ASIO. And I ran the test to 2% mean average deviation. So this is, literally tens of millions of orders were sent to get these statistics. Look, you can see, look at the X scale, so the Y scale. 1 times 10 to the 7, that is tens of millions. So if we add that together, there's probably 100 million orders were sent. to get these statistics. Look, the fastest is down to below 10 microseconds. The slowest message is 100, 2 milliseconds. So there's a lot of outliers here, but long outliers, but we can see that clearly this major area, they overlap. Okay, I did lots of optimizations. I really tuned the heck out of the code. And if we look at this graph, we can see performance on the left, and this is latency, so higher is worse. It takes longer to do something. I don't like that. I want a lower figure. And on my X scale, we've got compiler version with older compilers on the left, with the Clang batch on the right. And we can see on the left, we can see a steady improvement in performance as I did my compiler optimizations and I worked really hard and sweated. And I got from, here we can see just below 90 microseconds. I managed to get it to about below 60 microseconds, a 30% performance improvement. Really impressive, 30%. But then compilers come along. Look, GC6.3, major plus. Code generated by it was awful. And then we see no real performance improvement because basically I wasn't implementing optimizations. And I realized that, hey, wow, compilers having a major impact on the performance of the code. The lower graph is the performance of the simulator, the Exchange simulator. The upper graph is so that's the round trip of the simulator to take an order and send a fill from the binary format. The upper graph is when my client sends a new order, fixed new order, and receives a fixed fill. So we can see if we subtract the two, that's the time for my latency within my code. Fine. We can look at this, and as we go along to the right, we see major performance losses around GC7 series and 8 series, and then it improves 8.2, but then it reduces again. We see newer compilers a slight performance improvement. By the way, that performance improvement was an improvement in the implementation of Boostazio and has nothing to do with the compiler. What's happened is GCC's performance has dropped by 30%, the generated code. This is horrific. I hope people who are implementing GCC are listening to this and are shocked, horrified, embarrassed, and come at me with rage so I can explain it to them. Now we look at new versions as we move to the right of Clang. You see that hump at the right, that's Clang coming in. Because just to the left is GCC 10. We can see Clang. Clang is slower, those earlier versions of Clang. Newer versions of Clang, the performance increases. We see variability. But the newer versions of Clang are the same speed as GCC. So now GCC generates code just as bad as Clang is. This is not good. Right. What are the latencies? What are the histograms behind this? The histograms are key. And here we see the histogram. Again, we can see 3 times 10 to the 6 orders. Literally millions of orders were sent. We can see our mean is about 14 microseconds. Our standard deviation is 2. Okay, why is it 14 microseconds versus 60 microseconds? The 60 microseconds is the full round trip time for the client, from client sending a fixed message to receiving the fixed response. So this includes local host networking. Whereas this was taken, a message is received inside my translator, so it comes off the network buffer, timer starts. Is sent to the simulator, timer stops. Message is received from the simulator, comes off the buffer, timer starts, is sent back to my client, put onto the network socket, timer stops. So we can see this is measuring a much smaller time period than previously. So that's why we see it's 14 rather than, about 70 microseconds. We can see here we've got heartbeats occurring because what happens is the protocols for these exchanges is ridiculous. It's over TCP/IP. They heartbeat over TCP/IP. It's mad, but that's life. So we see the heartbeats, the sends and receives. Here we see our major orders and the responses coming in. We see the peaks. And we can see, I decided Is there an impact if I use RDTSC to start and end of the blocks that I wish to measure time for, or do I use CPU ID RDTSC and RDTSCP to measure it in order? And we can see there is a statistical difference in the histogram, in the kurtosis. There's no performance difference, but the kurtosis has changed materially. And we can see that when we use the in order, the CPU ID, RDTSC, RDTSCP, we can see the peaks are much narrower and sharper than without, which is what we would expect. The out of order is out of order measuring, so of course we're going to get lots more jitter in that. Okay, what about NUMA control? Let's pin. Well, I didn't pin. What I did is I just used NUMA control to say I'm going to use I had 2 CPUs and I'm going to use CPU 1 and that memory bus. And what we could see is there was a major difference. Look at those heartbeats. Again, look at the new order and the response. It's just sharper and cleaner. Mean hasn't changed. But remember that these means are computed as if this was a standard deviation, when it clearly isn't. It's not even a Poisson distribution. RDTSC alone consistently overestimates performance. So if somebody's quoting latencies to you and saying, oh, I used RDTSC, you know they're likely to be overstating the performance. RDTSCP, the in order, will give you a more accurate measure, as you can see from this graph. Now, here's the topology of my hardware. And what I did is I then pinned each thread to a core. So I've got cores allocated rather than leave that to the CPU. So NUMA node 1, I've now got each core is pinned to a specific task. With pinning, when we add it, as we can see here, the green is pinned, and we can see that our mean has reduced. We can see clearly it's had a major impact on the histogram and the impact of the histogram. We've got a major peak occurring around the 11 microsecond mark. Also, if we look at the outliers going back, look, the outlier here with just NUMA control and leaving it to the processor was 200 microseconds. If I pin, I'm up to 400 microseconds. And remember, I've spent millions of orders down this, so this is statistically significant. So what's happened is pinning has actually increased my maximum outlier latency. Pinning the threads, rather than leaving it to the processor. Very interesting. Okay, now we're coming on to the easy stuff. Few minutes to go. We're getting towards the end, don't worry. What about the comparison of compile times? Remember, I'm writing this code. I need to beat the competition. Beating them is not just fastest to the is not just fastest running. It's also fastest to the market. So the time it takes my compiler to run is an impactful factor. And we can see GCC on the left, Clang on the right. Clang is significantly faster in compiling the same code that GCC is. It's about 8 times faster. If anybody tells you that modules will give you an 8 times performance improvement, please, I beg you, show them this graph. Modules is useless for performance. What is required here, in my opinion, is there are implementation sub-optimizations in GCC that need to be seriously addressed, because clearly Clang can compile the same code roughly 8 times faster, generating output that's just the same performance, because remember, GCC now generates really sucky 30% slower code, right? Just as fast. You know, imagine GCC has magic modules in it. It's now compiles 8 times faster, as Bjarne is telling us, and the rest. Oh, it's compiling at the same speed as Clang with no modules. Yeah? That major performance loss in GCC around 8.1 to 8.2 is I actually re-implemented some template metastate machines with using from boost MPL vector to varadic templates. Voretic templates slow your compile time for this benchmark. One needs to be very careful. Okay, what about compiler errors? Remember I said clangers, little break? Problem is everyone thinks that compiling is easy. No, it isn't. If you change your compiler, what about your libstandard C++, libcxx? The problem is if I included libcxx, my entire operating system is predicated on using GCC. So Boost is built using GCC. So I need to rebuild all my third party to use Clang's libcxx. Life's too short, I'm sorry. Also, there were defects. Clang is, all compilers aren't perfect. And when you're using Clang with libstandard C++, not its own standard library, clearly it may have issues, which is not unreasonable. And there were issues, and I had to do magic fixes. Painful. Yes, Clang does also give error novels as well. Right. We'll need to push on a bit. I'm sorry, I'm overrunning a smidge. I do apologise. I will push through this quickly. The slides are available and all of this is online, so you're not missing out on anything. I looked at operating system and hardware choices. I will skip the details in this slide. I'll go on to the results, and then what you can do is you can look at the details later. Here are the results. Right. What we've got here is we can see CentOS, we've got various operating system versions. I just installed off the straight ISO image. So I didn't even install, I just ran it off the ISO image if I could. This is on a Haswell-based processor, Core i7, overclocked to 4.5 gigahertz. It would eventually overheat with memory issues after about an hour and crash. It was pushed so hard. That's what you do. C-states were removed, everything. And we can see the operating system has a major impact on the performance of my code. People think it's 4%. Well, I'm sorry, CentOS 6.9. Look at that. Look at that incredible performance difference between far right Gen 2. I mean, it's ridiculous. What, 4 times slower? Again, Ubuntu's low latency kernels are slower than the generic kernels for this benchmark. You can see there's mean average deviations have been added to these, so these are all statistically significant results. Okay. What about the comparison between my ancient AMD and the new Intel Core i7? I'm not banging against Intel and AMD. No, this is just different hardwares. One's really ancient, one's much newer. And we can see, surprise, surprise, the much newer one is significantly faster. Why? My code has been tuned for newer processors. All those AVX instructions are now being filtered through that well-designed Core i7, right? Whereas the old AMD with the bolted-on AVX, it's all a bit creaking. But you can see that this has had much greater impact than the operating system, which had a much greater impact than the 30% improvement in all my micro-optimizations. What about the impact of hardware bugs? Here we can see pre and post Spectre mitigations for CentOS, and we can see there is a significant impact in the mitigations have. On the left, we can see roughly 10%, 12% impact. Statistically significant impact. Again, what about Ubuntu? Likewise, we can see major impact on performance of the order of about 10%. Gen 2, likewise, similarly impacted. Notice the link, the full round trip. We've gone from about 22 microseconds up to about 28 microseconds. So what we've got a very complex situation where profiling is really important, and it takes an absolute age. Remember, I'm running hundreds of millions of orders. This takes days. The time of the critical code, and you've got to experiment with removing parts. Unit tests are utterly vital because when I'm removing bits of code to make it faster, the problem is I might break how the code runs. We need to record the performance and maintain SLAs. Highly tuned code is clearly very sensitive to versions of the compiler and operating system. Choosing the right compiler is really hard. Remember, some of them can optimize certain optimizations really well, but the same optimization used differently can be a major sub-optimization. Performance impact. I'm talking about the difference between const expra compiling out and not, and this is a major impact. Again, we've got the differences. GCC 7 and 8 are slower than GCC 6. 9 and 10, if you use newer versions of ASIO, speed up a bit, but they're still very slow. Clang has a very stable performance. The OS has equivalent impact or even greater impact than the choice of compiler. The effort spent on massaging code is significantly smaller impact than the compiler or OS choice. Choose wisely. Again, the mitigations we saw for the Spectre and Meltdown. We saw 12% impact, Exubuntu 5% impact. By the way, these figures have been checked by Intel. When I released these figures a year or so ago, they called me up and I spent 3 hours on the phone with Intel going through my methodology, and they said, yes, we agree. Your methodology is acceptable, appropriate, and we agree with your results. They match ours. It's extremely important to verify any performance impact. Remember, I said we're going to ignore Dijkstra's first maxim, premature optimization is the root of all evil. We'll set that aside. Now we'll take a step back. We're coming out of the rabbit hole. We're refreshed with this new knowledge, looking around and realizing, understanding that for certain benchmarks, things can get very, very, very hairy out there. It's almost like quantum mechanics and the Heisenberg uncertainty principle. There are details regarding regulation in the UK, because remember that the finance environment is a highly regulated environment. Final thoughts, exactly. Discard Amdahl's law at your peril. Please, I beg you, profile first. Do not try and double guess. Choose your optimization strategies really careful. Upgrade the hardware if you can. Choose your operating system very carefully. Remember, as well, the problem is that I write my application. It runs really well on that operating system and that hardware. But hey, it's not only one application that runs on it. It may be others. In HFT, it's only one. But we've got the real world we're talking about here, not just finance in the city. So therefore, HFT is not the be-all and end-all. But the takeaway here, the key point to remember is that you can have your code, when it's running on a platform, can be very surprisingly impacted by the operating system by a significant margin, by the hardware by a significant margin, by the compiler by a significant margin. Do you see? Also, you can get huge technical debt, all that customized code, that template metaprogramming to schedule the instructions perfectly. What happens if I change my hardware? That now may be suboptimal. Third-party libraries, Boostasio. People were telling me, Jason, but surely what about Boostasio? It's Boost. It's very general purpose. It's maybe it's got some sub-optimizations because of its genericity. Verification has demonstrated that this is not the case. Third-party libraries can be as fast as custom-designed code. More information, blah, blah, blah. And here, of course, are my links. So, ladies and gentlemen, thank you very much for your time. Thank you very much for your patience. I apologize that I overran by 10 minutes, but it has been quite interesting doing a first online talk. I welcome any questions.
Thank you, Jason. It was super wonderful and super interesting. I think we will move now to Zoom room for discussion. Is that
Okay, thank you. Right.
correct, guys? Okay. So let me just ask you a couple of questions first, and then we can move to the
Sorry,
discussions.
just a moment. To be clear,
Sorry?
I'm trying to find my Zoom room.
No, we can just discuss it here for now, and then we can move
Perfect.
to the. Okay, so there is a couple of questions from the audience during the talk. Um, so we actually discussed a lot branch prediction. So to be clear, you are talking about the branch prediction from the compiler, right? Is that correct?
Both the compiler perspective and the hardware perspective.
Okay.
Branch prediction, if people maybe people aren't familiar with branch prediction, let me
Oh, they're actually
just go
quite
back to my
familiar.
slides. Let me go back to my slides and try and skip. On. Anyway, where are we? Here we are. I want to get to the beginning, to that diagram of the processor, the bulldozer processor. So just bear with me. I will get there in a second. Can we do that? Bingo. The big stall is when it's trying to show the image. Now, the point is that when I generate software, I've got an if statement. The if statement, of course, being conditional, is what happens is in the pipeline flow. Sorry, I'm trying to find that diagram and it's just not appearing. In the pipeline flow, the if statement appears, and when it's executed, we can either execute the bar 1 or bar 2, the if or the else. Now, the issue is, right, got to the beginning. If I mispredict, branch predictors occur very early in the pipeline because the point is they want to predict accurately which branch to go down. The problem is if I mispredict, I need to roll back. Here we are. Do you see the branch predictor at the top right of this diagram?
Yeah.
So what happens is this predicts, say, for example, in my if bar 1, bar 2, else bar 2, it predicts I will go to bar 2. So what happens is, based on this prediction, my instructions are fetched for bar 2, go down to the pre-decoder, dispatch, get executed in the schedulers. But remember, my condition is being executed in one of these schedulers. The condition evaluates, and it evaluates and says, oh no, it's bar 1. This means that I need to roll back the results of computing bar 2, and I need to start refetching at instruction fetch at the top from bar 1. You can see that there are many stages in the pipeline, this rollback. The misprediction issue is a major performance impact for superscalar processors. Their branch predictors are roughly 96% accurate. The actual accuracy is, and the way they're implemented is highly confidential, commercial confidential, because of the impact in performance. And it's, as I said, roughly about the number of stages of the pipeline, which is about 20 stages. That's 20 clock cycles just to start reissuing instructions down this pipeline. Of course, I may have data cache misses. That's a serious problem. Now I've got to fetch from bar 1. I may have an instruction cache miss. That's going to be thousands of clock cycles going to main memory, data cache misses, again, many clock cycle loss. So we can see that despite the fact I say it's 20 clock cycles, it could actually be, on average, hundreds of clock cycles. So we can see that positioning the if and the else, the bar 1 and bar 2, is absolutely fundamental to the performance of my code.
Okay, thank you. I'm afraid we're out of time. We need now move to Zoom room. So we will wait you there. Thank you so much. It was a wonderful talk. Thank you.
Thank you very much.